Welcome viewers, in this video we will see the general block diagram of the demultiplexer. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, the block diagram of the demultiplexer. A demultiplexer is a circuit that receives information on a single line and transmit this information on one of the 2 to the power n possible output lines. So only one input line with 2 to the power n possible output lines. The selection of specific output line is controlled by the value of n selection lines, right? So what we have, 1 is to 2 to the power n with n selection lines. This is the general structure of the demultiplexer. Only one input, 2 to the power n output. This 2 to the power n output is controlled by the n number of selection line. This selection line will decide with the n number of outputs. So that is the structure of the demultiplexer. The diagram shows the block diagram of the demultiplexer. It has one input data line, 2 to the power n output line, and n selection line, one enable input. So these are all the things available in the block diagram. Now we'll refer the block diagram of the demultiplexer. So this is the one data input, D in. Enable input is available. So if the enable is 1 mean the demultiplexer will be enabled. If it is not needed mean we'll make the enable as 0. This is the outputs, y0, y1, y2 up to 2 to the power n minus 1 outputs. These are all the selection lines. S0, S1, Sn minus 1 selection lines. So this one input will be divided into n number of outputs that is controlled by this selection line, right? So we know that 1 is to 2 to the power n and n selection line. Let us consider n equal to 2. So 1 is to 2 to the power 2 with 2 selection line. That is 1 is to 4 and 2 selection lines. Let us consider this example demultiplexer. 1 input and 4 outputs. This is controlled by 2 selection line. Let us consider D in is the input data, right? So Y3, Y2, Y1, Y0 is the output. These are all the output, possible outputs. How it is controlled? It is controlled by the selection line, S1 and S0, 2 selection lines, right? 1 input, 4 outputs and 2 selection line. These selection line will decide the output. For example, the selection line is 0, 0 mean Y0 will be data available. The input data available in Y0. Remaining things are 0. If selection line is 0, 1, then the data available in Y1. Remaining things are 0. If the selection line is 1, 0, data available in D2. The remainings are 0. Right? If the data line is 1, 1, the data available in Y3. Remainings are 0. Right? So this is the possible output for n equal to 2, 1 is to 4 demultiplexer. Right? So these 4 different output we are getting 0, 0, 0, D in, 0, 0, D in 0, 0, D in 0, 0, data in 0, 0, 0. How it is possible? That is based on the selection line 0, 0, 0, 1, 1, 0, 1, 1. So this will provide these 4 possible selection line. 2 selection line with the 4 possible option will make the 4 different outputs, right? So this is the example for 1 is to 4 multiplexer, right? One more block diagram is available. So this is the 1 is to 2 to the power n tmax, the input data enabled. So it is given as a switch. So the data in, these are all the outputs. So it will be connected according to the selection line. Either it will connected to Y0, Y1 or Y2 up to Y2 to the power n minus 1. It is given in a like a switches, right? So the corresponding any one, this input data will be connected to any one of the output. That is based on this selection line. So in this video we discussed the general block diagram of the demultiplexer. Demultiplexer is 1 input, 2 to the power n output and n selection lines. We discussed one example. If n equal to 2, it become 1:4 demultiplexer with 2 selection line. We discussed the truth table also. Also, we discussed the block diagram with the switches. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the differentiate between multiplexer and demultiplexer. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The difference between the multiplexer and demultiplexer. So here we'll have the first column parameters available. In the second column we'll see what is available in multiplexer. Third column demultiplexer. First definition. What is the definition of multiplexer? Multiplexer is a digital switch which allows digital information from several sources to be routed onto a single output line, right? Several inputs with a single output, right? So 2 to the power n inputs with only one output. That is the basic definition of the multiplexer. Multiplexer means multiple things are available but the output is only one, right? In that what we need is n selection lines. We need n selection lines, right? So this n selection line will decide which of the inputs should be available at the output, right? This control is done by the selection line, right? N number of 2 to the power n number of inputs, only one output, that is controlled by n selection lines. Then demultiplexer, that's the opposite. Demultiplexer is a circuit that receives information on a single line, only one information, and transmit this information on one of the 2 to the power n possible output lines, right? One information that is converted into 2 to the power n possible outputs, that is the available in the demultiplexer, that is 1:2 to the power n with n selection lines, right? Just opposite to the of the multiplexer. Only one input is divided into n number, 2 to the power n number of outputs, that is controlled by the n selection lines, right? So this is the basic definition. Now we'll see the other parameter. What are the other parameters available? So the number of input is 2 to the power n. Here only one. Number of output data is here 1. In demultiplexer only 1. Demultiplexer 2 to the power n, right? So 2 to the power n is to 1 input. This is one output. Here one input, 2 to the power n output. Relationship of input and output. Many to 1. Many to only one output. One to many. One input is converted into many outputs, right? What are the applications? That is very important. Used as a data selector. N number of inputs are there. In that we will select the particular data. For example, if you want to play the song is available, maybe available in the mobile, or maybe available in the system, or maybe available in the USB, whatever may be, it can be played in a player and you can listen in the speaker, right? So the data may be available, the song may be available in different devices, but final output is only one. We can play the song and listen in the speaker. We can play from the computer or USB or from the mobile, whatever may be. So it is used as a data selector. We can select any one device. Used as data distributor. One data is distributed to many lines. There is a distributor. It is selector. Many data is available, in that we are selecting. Here only one data is available, that is distributed. In time division multiplexing at the transmitting end. At the transmitting end, it is also a time division multiplexing. At the same time here, in time division multiplexing at the receiving end. At the receiving end, we are using the demultiplexer because 2 to the power n outputs are available. Here 2 to the power n inputs are available at the input end, transmitting end is available in the receiving end. So we can go for a time division multiplexing at transmitting end, that is 2 to the power n inputs, at the receiving end, that is 2 to the power n outputs, right? So this is the application of the multiplexer and demultiplexer. So in this video we discuss what are the parameters similar and difference between the multiplexer and demultiplexer. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the details about 1:4 demultiplexer. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic 1:4 demultiplexer. Demultiplexer is nothing but having one input and 2 to the power n output. One input and 2 to the power n output, and having n number of selection lines. This selection line will decide the how this selection line is used to produce the 2 to the power n outputs. From one input, 2 to the power n outputs are produced by the selection line. So here 1:4 means it is 1:2 to the power 2, n equal to 2 here, right? So that we have two selection lines. One input, 2 to the power 2 means 4 outputs, and two selection lines are available in the 1:4 demultiplexer, right? Now we'll see the diagram show 1:4 demultiplexer. We'll see the diagram later. The single input variable is din, has a path to all 4 outputs, right? The single input is din. Din is nothing but a input data that is connected to all 4 outputs, but the information is directed to only one of the output line depend upon the selection line, right? The input is connected to all the circuit, but which one is enabled, that is decided by the selection line. And also we have enable input should be high to enable the demultiplexer. If enable is high, the circuit will be activated. If enable is 0, circuit will be deactivated, right? So we have one input, 4 outputs. This one input is routed to 4 outputs based on the selection line. The selection line will decide which one will be available as the output out of 4. Then also we are having the enable input. Enable input enable the demultiplexer, otherwise the multiplexer will be deactivated. Your enable input is 0. Now we'll go to the truth table. 1:4 multiplexer, the truth table. So this is the enable input E. The selection lines, selection input S1 and S0. This is the input data DN. This is the output Y0, Y1, Y2 and Y3, right? The Y0 is the LSB, Y3 is the MSB, right? Enable, selection input and outputs. If enable is 0, whatever may be the selection line, whatever may be the data input, all outputs are 0. That is, circuit is not enabled. It will produce only 0. Suppose enable is 1. In that case, we will go to the remaining. Here, all are enable is 1. So the selection line 2 bit data S1 and S0. So that 4 combinations are available: 0 0, 0 1, 1 0, 1 1. In that 0 0, again there are 2 possibilities. The data may be 0 or 1. The data may be 0 or 1. So that we have 8 possibilities are available. First we will see the 0 0, first combination. 0 0, if the data input is also 0 means all are will be 0 only. Suppose the data input is 1 means the first position will be 1. Remainings are 0. The input data 1 is routed to the first position if the selection line is 0 0, right? D in is routed to Y0, right? We have only one input. That input is may be available in first position or second position or third or fourth position. For 0 0, the input 1 is available at the first position. Then we'll go to the next one. 0 1. Input is 0 means everything will be 0 only. For 0 1, input is 1 means it is the input is routed to the second position Y1, 0 1 0 0. See here it is 1 0 0 routed in the first position Y0. For 0 1, the input is routed to the second position Y1, right? So that we got 0 1 0 0. Then third combination 1 0. If the data is 0, totally everything will be 0. If the data is 1, then input is routed to the third position, y2, 0, 0, 1, 0. Right? D in is routed to y2. The last combination, 1, 1. If the data is 0, everything will be 0 only. If the data is 1, it is routed to the fourth position, y3, right? 0, 0, 0, 1, right? So we have only one input. For 0, 0, it is routed to first position, 1, 0, 0, 0. Second combination, 0, 1 means 0, 1, 0, 0. Third means 0, 0, 1, 0. Fourth means 0, 0, 1, 1. Right? See, this 1 is available in first position, second position, third position and fourth position. Right? So available one input is placed in the 4 different combination, that is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That is, input is positioned in first position, second position or third position or fourth position. So that we got the 4 different output. Right? So for the first position it is 0, 0. For second position 0, 1. Third position 1, 0. Fourth position 1, 1. Right? So based on that we will see the logical expression and logical diagram. So this is the logical expression. 0, 0 means S1 bar, S0 bar. 0, 1 means S1 bar, S0. 0 refers bar complement. 1, 0. 1 means S1, 0 means S1 bar. 1, 1 means same it is S1 and S0. Right? So in the every case we have D in is a input. Now we will see the logic diagram. So we have the selection line S0 and S1. This green color is the selection line. This red color is the selection line S1. This is S0 and S1. Right. So with the tapping is taken and one NOT gate is connected. So that S0 mean after the NOT gate we got S0 dash. Similarly in the S1 one tapping is taken and is connected to the NOT gate. S1 means after the NOT gate it is S1 dash. So we have 4 possibilities. S0, S1 is available. S0 dash, S1 dash also available. Using the NOT gate we got the complement also available. So this is the data input DN. Right? We have 4 AND gates are available. 4 AND gates are connected in order to produce the 4 different output. Right? So in the all 4 AND gate the DIN is connected. Data input is connected. Right? The one input is data input. And also it is connected with the enable line. So it is enable. Enable line is the second input. If the enable is 1, then only they will produce output. If enable is 0 means because of NOT gate every output will be 0. Right? Enable should be 1. Right? So we have 4 input. Out of 4 input, one input is the data line, second input is the enable line. Right? Third and fourth input is this selection line S1 and S0. We will see how it is produces. Right? So we already discussed why not placed in first position mean the input will be 0, 0. The selection line will be 0, 0 means the Y naught will be activated. Right? If it is 0, 0, S1 is 0 mean S1 bar will be 1. S0 is 0 mean S0 bar will be 1. Right? For a selection line 0, 0, we got the Y0 output. 0, 0 means S1 bar and S0 bar become 1, 1. Already enable is 1 and DIN is available. Right? So all 3 inputs are active high. So the DIN will be available at the output. For that case 0, 0. Right? Because we are connected in such a way that 0, 0 means it is connected with complement S1 bar, S0 bar. So that 0, 0 automatically become 1, 1. Right? But second case 0, 1, 0, 1. In that we are getting the second output. We already discussed in the truth table. 0, 0 mean first position, 0, 1 second position, 1, 0 third position, 1, 1 mean fourth position. The first position we discussed. 0, 1 means what will happen? S1 is 0 mean S1 bar will be 1. So S0 is already 1. Enable is also already 1. See this, S1 is 0 but we are connected S1 bar. Here S1 bar is connected. Right? So the S1 bar, this is the S1 bar is connected. S1 bar is connected, so that we are getting, so it's not connected here, it should be connected here. So it is here, here it is same, S0 and S1 is connected. So here it is connected with the S0. So we have all three inputs are active high, so automatically D in is available at the output in case 0 1. Now 1 0, if it is 1 0, right, see here S1 is connected, here connected with the S1, this is S1 and this is S0 dash, not here, here S0 dash is connected. So S1 is 1 means the S1 will be 1, S0 is 0 means S0 dash become 1, already enable is 1, right. So that automatically D in will be available at the output in case 1 0, right. The remaining will be automatically 0. For case 0 0, here this is will be 0, so automatically the remaining outputs are 0, right. So for 1 0 only this output will be available, remaining will be automatically 0, because AND gate any one input is 0, totally it will produce 0 0 0 1. We will see this 1 0 means, see here S1 is 1 mean S1 bar will be 0, so totally it become 0, right. So for this combination only one this output will be produced, other outputs are 0. The finally we have 1 1, so it is connected directly S1 and S0, so it is connected direct, so this is correct only, this is correct, here also correct, this is connected S0 and S1, right. So already enable also 1, S1 also 1, S0 also 1, so automatically we get D in as a output, right. So in this case S0 is 1, so S0 dash will be 0, so this gate will be the output of AND gate is 0. Similarly here S1 is 1, S1 bar is 0, so this output also 0. Here both are 1 1, so while taking complement it becomes 0, both are, the output will be 0, right. So for this combination only this NOT gate will be produced, this AND gate will produce the DN, remainings are 0. Similarly for 0 1 only this AND gate will produce the output Yin, remaining outputs are 0. Similarly for 1 0 this NOT gate will produce DN, third position, remainings are 0, right. Similarly the fourth, for combination 1 1 this AND gate will produce the DN output, remaining output 0. For example 0 0 mean this output will be 1, remaining outputs are 0 0 0. For second combination this output is 0, only this output will be 1, remainings are 0. For third combination this output will be 1, remainings are automatically 0. For fourth combination only this output is 0, remainings are 0, because it is connected S1 bar S2 bar, right. S1 and S0 is 1 mean automatically S0 becomes 0, so total is 0. Here one S0 S1 dash is S1 bar is there, so that also 0, right. So because of the connection, based on the connection S1 or S1 bar, automatically the remainings are 0, right. So for 0 0 we got this 1 0 0 0 first position, 0 1 means we got the output at second position, 1 0 mean we got the output as third position, 1 1 mean we got the output at fourth position. So in this video we discuss about how to the working principle of the 1:4 demultiplexer, having one input and 2 to the power 2, 4 outputs. So this one output is routed to the 4th position, either first position or second or third or fourth position, that is decided by the selection line. We discuss the truth table, then we frame the Boolean expression, that expression is implemented with the logic gates. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Viewers, in this video we will see the 1:8 demultiplexer. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic 1:8 demultiplexer. That is, a demultiplexer means it is 1:2 to the power n, one input and 2 to the power n outputs with the n selection lines, right. This one input is produced as a 2 to the power n output, that is based on the selection line. Selection line will decide how this one input is converted into 2 to the power n output. So in this case here we have 1 is to 2 to the power 3. The n is n equal to 3 here. So that we got 1 is to 2 to the power 3 means 1 is to 8 demultiplexer. So we have 3 selection lines. So these 3 selection line will decide out of this only one output how we are producing the 8 different outputs, that is decided by the selection line. So the diagram shows the 1:8 demultiplexer. We will see the diagram later. The single input data is the DIN. DIN is the single input data. Has a path to all 8 outputs. The single input data is connected to all 8 outputs, but the input information is directed to only one of the input line, depends upon the select input. So we have only one single input data DIN that is connected to all 8 possibilities, but in which circuit the output will be available, this DIN will be available, will be decided by the selection input. In out of 8, only one position only the input data will be available, whether it is first position or second position will be decided by the selection line. Now we will see the truth table, how the data is routed to 8 different positions. So this is the enable input. So if the enable is 1, then only the circuit will be activated. If enable is 0, circuit will be deactivated. Then the selection lines, we already discussed there are 3 selection lines, S0, S1 and S2, right. Then this is the output, 8 different output, 2 to the power 3, 8 different output, Y0, Y1, Y2 up to Y7, right. If the enable is 0, whatever may be the selection line, the output will be 0. So circuit is not activated. Suppose enable is 1, for other cases the enable is 1, that is the circuit is now activated. So here the selection line having 3 inputs, so that 8 combination will be available, 2 to the power 3, 8 combinations are there, 0, 0, 0, 0, 0, 0 means this is the input data DIN, the input data available in the first position, remainings are 0, right. For the combination 0, 0, 0, the data is available in the first position, the remainings are 0. What is the expression for that? There are 5 inputs available. While developing the logic gates, the 5 inputs. One is enable. If enable is high, then only it will produce the output. Another one is data in. Remaining 3 is the selection line. See this how the selection lines are given. 0, 0, 0 mean it is taken complement. S2 bar, S1 bar, S0 bar. So 0, 0, 0 mean while taking complement automatically it become 1, 1, 1, right. So enable is 1, then S2 is 1, S0 also 1, S1 is also 1 mean the data will be available in the first position, right. All the inputs are 1 because it is connected to the AND gate, right. So for 0, 0, 0 automatically we are connected with the complement, so that it become 1. Then the next combination 0, 0, 1, second combination mean it produces at the second position, the input data available in the second position, the remainings are 0. So see here also 0, 0, 1, first 2 zeros are available, so that first 2 selection lines are taken complement. The third one as it is, because third one is 1, so we connected as it is. So 0, 0, 1 means automatically it become 1, 1, 1, right. 0 is converted into 1, this 0 also converted into 1. So according to the selection line, here we are connected with the directly or with the complement. While taking complement, automatically these zeros become 1, right. So that is the logic available here. The third combination 0, 1, 0 mean the data available in the third position, remainings are 0. So accordingly this logical expression also available. Fourth combination 0, 1, 1 mean the data available in the fourth position, remainings are 0. 1, 0, 0 fifth combination, the data available in the fifth position, remainings are 0. 1, 0, 1 sixth position, sixth combination, the data available in the sixth position, remainings are 0. 1, 1, 1 seventh combination, the data available in the seventh position, remainings are 0. Last one, eighth combination, eighth position, 1, 1, 1 means the data is available in the eighth position, the remainings are 0. right? So it is very simple. First combination, data available in first position. Second combination, second position, like that it is available. First position, second, third, fourth, fifth, sixth, seventh and eighth. So that we are getting 8 different outputs. So the single input is now produced with the 8 different outputs. But based on the selection line, we are having the complement, so that the data will be high. All the inputs will be high, so that will produce the input at the first position, right? So now we need to implement this logical expression using the logic gates. Before that, we'll see the block diagram of the 8:1 multiplexer. This is a data in, only one input data. Enable is available, only one enable. If the enable is 1, the data, the circuit is activated, otherwise 0. We have the selection lines, 3 selection inputs are available, S0, S1, S2, right? So we already discussed 0, 0, 0, first position, first combination mean Y0 will be available at the output, remainings are 0. 0, 0, 1, 0, 0, 1 means that is 0, 0, 1, this is 1, right? This is the MSB. 0, 0, 1 means Y1 will be available at the output, remainings are 0. Like that, there are 8 combinations available here. Accordingly, 8 output. Out of 8 output, any one will be available at the output, remainings are 0. Right? So what we discussed in the logical, the truth table, that is available, that can be correlated with this base block diagram, right? So only one input enabled, then this 3 selection lines. Based on the selection line, the D in will be available in first position or second or third up to 8 position. 0, 0, 0 mean D in available in the first position, remainings are 0. 0, 0, 1 means D in will be available in the second position, like that it will go. Now we will go to the logic diagram. So in this logic diagram, so the 3 selection lines are available, S2, S1, S0. This line represents the S2 line. This is S1 line, this is S0 line. From S2, one tapping is taken, connected to the NOT gate, so that we got S2 dash, right? Here S2 available, after NOT gate we got S2 dash. Similarly, S1 also connected with the NOT gate, so that we got S1 dash. In S0 also one NOT gate is connected, so that we got S0 dash. So all 6 possibilities available, S2, S1, S0, S2 dash, S1 dash and S0 dash is available. This is the data input, D input, right? Because of 8 output, we have 8 different AND gates are available. 8 AND gates are available. In all 8 AND gates, the data is connected. The data input is connected. This is the data input, right? This we have one more input, enable is available. We already discussed, if enable is 1, then only the circuit will be activated, otherwise circuit will be deactivated, right? So this enable is connected in all the AND gates, right? So AND gate, there are 8 AND gates available having 5 inputs. This first input is nothing but a data in. So everywhere data in is connected. The last one is nothing but enable, that is connected to every NOT gate. Remaining 3 is nothing but a selection lines, right? According to the combination what we discussed, these selection lines are connected. Now we'll see these selection lines one by one. We'll start from the Y0. We'll go to up to Y7. First we'll go to Y0. Right, this is the Y0. Here first one is the data input, last one is the enable. Then here the selection lines are connected, S2 dash, S1 dash and S0 dash. So this is the first combination, 0, 0, right? So S0 dash is connected, S1 dash is connected and S2 dash is connected, right? Suppose this is the combination 0, 0, 0, right? We already discussed in the truth table. For 0, 0, 0, it is connected with the complement. So that for 0, 0, 0, it is connected with the complement. So 0 means S2 is 0 means S2 bar will be 1. S1 is 0 means S1 bar become 1. S0 is 0 means S0 bar become 1. Already enable is 1. So automatically it will produce the Y0 is nothing but a D in. The D in data in available in the Y0, right? So this is the first combination 0 0 0, but we connected with S2 bar, S1 bar and S0 bar. So the 0 0 0 become 1 1 1, right? So automatically all inputs are 1. So the DN will be available at the output, Y0. What about this Y1, Y2, Y3? This is automatically 0. We will see that. S2 is 0, right? So see this one S0 is, what is the value of S0 is 0. So S0 0 mean automatically everything will be 0 because of NOT gate. Similarly, see here S1, what is the value of S1? S1 is 0, so this become 0. Here S1 is also 0, S2 also, S0 also 0, so totally 0. So based on that, 0 0 0 means only this AND gate will produce the output DN. Remaining all 7 AND gates automatically become 0 based on this 0 value, right? Either S0 or S1 or S2 is connected, so based on that it become 0. See this, due to this S0, this NOT AND gate produce 0 output. Here this S1 is 0, here S1 also 0, S0 also 0. Like that, remaining AND gates produce only 0 output, right? Only Y0 will produce the output with DN. Similarly, we will go to the remaining combination. Second one 0 0 1, right? So 0 0 here complement is available, so it become 1 1 1. Already enable is 1, so that DN will be available. So that in the Y1 DN will be available. The data available in the second position. What about this remaining AND gate? We'll see one more here. See this S1 is, what is the value of S1 here? 0. So this value is 0 mean totally it becomes 0. So the remaining all AND gate will produce only 0 output. So here also we can see here S0 is 1, so S0 bar will become 0. So totally it becomes 0. Then we'll go to the third combination 0 1 0, right? So here the bar is available, so 0 become 1. This is 1 as it is. Here S0 is 0, so S1 bar become 1, already enable 1. So automatically Y2 is nothing but the output. The output Y2 is nothing but DN, data in available in the Y2. Then we'll go to the next one 0 1 1, right? Here bar is available, so this 0 become 1. These two are as it is, already enable is 1. So all are 1, so data in available in the Y3. We'll go to the remaining combinations. So 0 1 1 is there, now it is 1 0 0, right? 1 0 0 means this one as it is, because here complement is there, so these zeros become 1, already enable is 1, so the DN available in the Y4. Then the next combination 1 0 1 0 1. So a small correction here, this is the bar, here the bar is not available, 1 0 1, right? So 1 as it is, this 0 become 1 because of complement, this is 1, already enable is 1, so automatically all inputs are 1, so the data in available in the Y5. The next one 1 1 0, right? The next combination, so here 1 1, this S0 bar, so that this 0 become 1, already enable is 1, so data in available in the Y6. The last one 1 1 1, right? So all are connected directly, so already enable is 1, so the data in available in the Y7, right? So out of 8 output, that only one data input is there based on the selection line. For example 0 0 0 mean the data available in the first position, 0 0 1 means second position, like that it will available up to 8 positions. That the selection lines are connected in such a way that 0 0 0 means S2 bar, S1 bar and S0 bar is connected, so that 0 0 become 1 1 1, so that the output of the AND gate is high, so it will produce the DN in the first position, right? So according to 0 0 or 0 0 1, the complement is connected, so that automatically the output will become high. In this video we discuss about 1:8 multiplexer, that is 1 input and 8 output. How this 1 input is produced as a 8 different output, that is based on the selection line. We discuss the truth table, block diagram, followed by the logic gate. We discussed the each and every output, how we got the output with the notation. We substituted the value 0001. We verified from Y0 to Y7. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the design of 1:8 demultiplexer using two 1:4 demultiplexer. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. We need to design the 1:8 demultiplexer using two 1:4 demultiplexer. We know that multiplexer is a device that having only one input, 2 to the power n output and n number of selection lines. So this is the basic structure of the demultiplexer. One input, 2 to the power n output and n selection lines. So here one input, the n is 3, 2 to the power 3, 8 outputs, and 3 n is 3 means 3 selection lines. Similarly here one input, 2 to the power 2, 4 outputs and 2 selection lines, right? So we have here 3 selection line, here 2 selection lines. This selection line will decide the output. Having one input with n number of output is decided by the selection line, right? Now we'll see this design step by step. Step 1, connect the D in. This is the input, only one input. Signal to D in input of both the multiplexer. So the input signal is given to both the multiplexers. So we are using two 1:4 demultiplexer to design 1:8 multiplexer. So both the multiplexer we connected the D in signal. Input signal is connected to both the demultiplexer. Now we'll see the selection lines. So there are 3 selection lines for 1:8 multiplexer. 3 selection line. Let us consider the 3 signals A, B, C. So this is the most significant bit. This is least significant bit. This most significant bit is used for enabling the demultiplexer. Because we have two 1:4 demultiplexer available, we need to enable one demultiplexer at a time. Another multiplexer is disabled. So the signal A is used for enabling the multiplexer. Then B and C used for selection line. For 1:4 multiplexer, we need only 2 selection lines. So B and C used for the selection line of the demultiplexer, both the demultiplexer, B and C. For example, B used as S1 and C used as S0, right? So the input D in is given to both the multiplexer. In this among A, B, C, three signals, in 1:8 we have 3 selection lines are there. In that, the most significant bit is used for enabling the demultiplexer. Then least significant bit C and B used for selection line of the 1:4 demultiplexer, right? So it is given here. Connect the selection lines B and C to select the line of S1 and S0 of the both the demultiplexer respectively, right? Now we'll go to the step 3. The connect most significant bit, that is A, such that when A equal to 0, dmux1 is enabled. Because A is equal to 0 means it is given in inverted using the NOT gate. So A equal to 0 means dmux1 is enabled. When A equal to 1, dmux2 is enabled, right? So now we decided the input D in given to both the multiplexer. Selection line B and C. Enabling the demux is A, right? So based on that, now we'll go to the diagram. So this is the logic diagram. So this is first demux 1:4 demux1. This is next demux 1:4 demux2. We are using two 1:4 demux, right? So this is the corresponding output Y0, Y1, Y2, Y3. Similarly Y4, Y5, Y6 and Y7. There are 8 outputs. So that we'll get 1:8 output. So the D in is the signal, input signal that is given to the dmux1 as well as dmux2. The input D in is given to both the dmux, right? And the selection line. This is 3 selection line for 1:8 multiplexer. In that but for 1:4 demultiplexer we need only 2 selection lines, so that the first one most significant bit is used for enabling the demux, right? If a is given through the NOT gate, let's say, so if a equal to 0, here it become 1, so demux 1 will be enabled. A equal to 1 means here 0, demux 1 will be disabled. This one is applied to the second demux. So if a equal to 1 means demux 2 will be enabled, right? So the signal a used for enabling the demux, either 1 or 2. This B and C is connected as a selection line for 1:4 demux. B is connected as S1, C is connected as S0, right? So input is given to both the demux. The most significant line signal A used for enabling the demux. B and C used for selection line of demux 1 and 2. Both demux 1 and 2, it is a selection line, right? So what will happen if it is demux 1 is enabled? It is 0 0 means we will get y0 as the output. 0 1 means y1 as the output. 1 0 means y2 as the output. 1 1 means y3 as the output. Similarly here, at a time only one demux will be enabled, another demux will be disabled, right? So based on that we'll go to the truth table. Now we'll see the truth table. So this is the truth table of the 1:8 multiplexer using 1:4 demultiplexer. Let's see the 3 selection lines A, B, C. 3 inputs of 3 selection line of the 1:8 demultiplexer. In that A used for enable. S1 and S2 used as B and C. B and C used as S1 and S0 as a selection lines, right? So this is the 8 outputs: A, Y0, Y1, Y2, Y3, Y5, Y4, Y5, Y6 and Y7, right? 1:8 outputs are available, right? If the enable, the signal A enable is 0, 0 means that demux 1 will be enabled because it is given through the NOT gate. So demux 1 is enabled, that is we will get the output from Y0 to Y3, that is A equal to 0. At the time demux 2 will be disabled. Demux 2 is disabled, we will not get any output. See this, when A is 0, this Y0 to Y3 will get the output. This Y4 to Y7 all are zeros. This is demux 2 is disabled, only demux 1 is enabled. In that, if it is B and C is 0 0 mean the out data available in Y0. 0 1 means data available in Y1. 1 0 means data available in Y2. 1 1 means data available in Y3, right? So we'll get the data Y0, Y1, Y2, Y3. These are all zeros. All outputs are zeros, right? Then if it is enable is 1, what will happen? Demux 2 will be enabled. Demux 1 will be disabled. So that will get the output from Y4 to Y7 when A equal to 1. See, this demux 1 is totally disabled. All are zeros. Demux 2 is enabled. In that, again it is 0 0. The selection line 0 0 mean we will get the output in Y4. If it is 0 1, we will get the output in Y5. 1 0, we will get the output in Y6. 1 1 means we will get the output in Y7. So we are getting the output from Y4, Y5, Y6 and Y7. These are all zeros, right? So by seeing the complete truth table, see that we got the output from Y0, Y1, Y2, Y3, Y4, Y5, Y6 and Y7. So this is the 8 different outputs, right? So we are getting the output of 1:8 demultiplexer by using the 1:4 2 demultiplexer. This is the total output of the 1:8 demultiplexer, having only one input with 2 selection lines. One is used for enable, another 2 used for the selection line, right? So first 4 output, demux 1 is enabled, 2 is disabled. Remaining 4 outputs, demux 1 is disabled, demux 2 is enabled. So that we are getting the corresponding inputs from Y0 to Y7. So in this video we discuss how to design the 1:8 demultiplexer using two 1:4 demultiplexer. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the implementation of 1:16 demultiplexer using 1:4 demultiplexer. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. We need to implement 1:16 demultiplexer using 1:4 demultiplexer. We know that the multiplexer is nothing but 1:2 to the power n with n selection lines, right? Only one input, 2 to the power n outputs with n selection line. This is the basic structure of the demultiplexer. This n selection line will decide the 2 to the power n number of outputs. From the one output we are getting 2 to the power n output, that is decided by n selection lines. So this 1:16 demultiplexer means it is nothing but 1:2 to the power 4 and 4 selection lines, right? One input, 16 outputs are available, that is controlled by 4 selection lines. 1:4 mean 1:2 to the power 2 with 2 selection lines, right? So this is having one input with 4 outputs and controlled by the 2 selection lines, right? Suppose we want to implement 1:16 multiplexer, that is 16 outputs we need, means here we are using 1:4 demultiplexer. So 4 outputs are available, but here we need 16 outputs. So we need to use 4 numbers of 1:4 demultiplexer. We need to use 4 number of 1:4 demultiplexer, so that 4 into 4 will get 16 outputs, right? So for both the case only one input, right? Here 4 selection lines are available, but here we need only 2 selection lines, right? So in this let us consider S3, S2, S1, S0. These are all the 4 selection line in the 1:6 multiplexer. In that the least significant bit S1 and S2 is used for the selection line of 1:4 demultiplexer. For all 4 demultiplexer we can use S1 and S0 as a selection lines, right? Suppose 0 0 mean it will select the dmax 1, 0 1 mean it will select the dmax 2, 1 0 means dmax 3, 1 1 means dmax 4. So the selection line will select out of 4, it will select any one dmax, right? What about this another 2 selection line, right? Here we are having 4 dmax. In order to select these 4 dmax, we need one more dmax. One more dmax is needed. So that dmax will select out of 4 dmax, it will select any one, right? So here we have 4 dmax, that is controlled by least significant bit of the selection line S1 and S0. That 4 demultiplexers are controlled by one more dmax is needed. For that one more dmax we are using this S3 and S2. That is the most significant bit, right? So we'll see the block diagram, you are able to understand clearly. So that is our basic concept. We'll see the description. The 1:6 demultiplexer have 16 outputs. To select one of the 16 output, the circuit need 4 selection lines. Each 1:4 demultiplexer require 2 selection lines, right? So connect 2 least significant bit S1 and S0 to select the 4 of 4:1 multiplexer, right? That what we discuss, S1 and S0, right? The step 2, second step is connect one more 4:1 demultiplexer such that 4 outputs are routed to the data input of 4 demultiplexer. Here we are using 4 demultiplexer, that is controlled by one more 4:1 1:4. It is a 1:4 demultiplexer, right? 1:4 demultiplexer. For that we need to connect the MSB S3 and S2, right? Now we'll go to the block diagram how we are connecting. So totally we are having 5 dmax, 4 dmax, that is controlled by one more dmax. Now we'll see the block diagram. See this is the dmax, second dmax, then third one, fourth one and fifth one, right? So that these 4 dmux are selected by one more dmux, is this one. So that is named as dmux 1. This is the fifth dmux. This dmux will select the remaining 4 dmux, so that it is named as dmux 1. But the data input is given, only one input. It is controlled by the selection line S3 and S2, MSB, right? Suppose it is 0 0 means the Y0 output will be available in Y0. 0 1 means output available in Y1. 1 0 means Y2. 1 1 means Y3, right? So this Y0 is connected to the dmux 2, right? This Y0 is connected to dmux 2. Y1 is connected to dmux 3. Then Y2 is connected to dmux 4. Then Y4 is connected to dmux 5, right? So this dmux will route the inputs, route the available inputs by to this 4 dmux, right? 0 0 means first one, 1 0 0 1 second, 1 0 third, 0 1 1 means 4, right? So these 4 dmux are controlled by this one more dmux with one data input. This data will be given to any one of this dmux based on the selection line, right? Now these 4 are controlled by this dmux. Now we'll see this control of this dmux one by one, right? So this is dmux 2, it is named as dmux 2. So when the selection line MSB S3 and S2 is 0 0 mean this dmux will be enabled, right? This dmux will be enabled, remainings are disabled. So it got the input, remaining inputs are 0, right? In this again, here we have 2 selection lines are available. These 2 are nothing but this is S0 and S1. It is connected to all the dmux. The selection line is connected to all. Here 0 0 mean this first data D0 will be enabled. 0 1 means D1 will be enabled. 1 0 means D2 will be enabled. 1 1 means D4 D3 will be enabled, or remaining all remainings are zeros, right? So the selection line 0 0 means the dmux 2 will be enabled. In that again 2 selection lines are available, 4 combination, based on that this any one of the data will be enabled, remainings are 0. Suppose the data line, the selection line 0 1 means dmux 3 will be enabled, right? In that again is connected with S0 and S1. 0 0 means D4, 1 0 means D5, 1 0 1 0 means D6, 1 1 means D7, again based on the selection line. Then the selection line S3 and S0, 1 0 means dmux 4 will be enabled. Again here it is connected with the MSB selection line S0 and S1. It is 0 0 means D8, 0 1 means D9, 1 0 means D10, 1 1 means D11, right? So then the selection line this 1 1 means this fifth dmux will be enabled. Again here see this S0 and S1 is connected. 0 0 means D12, 0 1 means D13, 1 0 means D14, 1 1 means D15 will be enabled. In that case remainings are 0, right? So we are having 4 dmux, so that we are getting 4 into 4 16 output. That is controlled by one more dmux, 1:4 dmux. That dmux is controlled by selection line S3 and S2. These 4 dmux are controlled by the selection line S0 and S1, right? So that we are getting 16 different output. Now we'll refer the truth table so that we are able to understand clearly. Now we'll see the truth table. Now refer this truth table. This is selection lines S0, S1, S2, S3. These are all the 16 different outputs starting from 0 to 15. 16 different outputs are available. We already know that S1 and S0 is connected to all 4 dmux. S3 and S2 is connected to the one more dmux. In order to control the other 4 dmux, this S3 is S2 is connected to the one more dmux, right? So in this S3 S2 is 0. If it is 0 means what happened? This dmux 2 will be enabled. Dmux 2 will be enabled. That is, we got the data from D0 to D3, right? So S3 S2 connected to the main dmux. If it is 0, the first demux, that is second demux, demux 2 will be enabled the data from D0 to D3, right? In this again there are 4 combinations. If it is 0 0, the data, first data will be available, D in available in the first position, 0 1 means second position, 1 0 means third position, 1 1 means fourth position. All remaining data are zeros. These demux are not enabled. Only this demux 2 is enabled. We are getting the data from D0 to D3 based on this selection line S1 and S0, right? Suppose if it is 0 1, next combination 0 1 means demux 3 will be enabled, so that we are get the data from D4 to D7, right? So this D4 to D7, this D0 to D3 is the first demux is disabled, third and fourth demux also disabled, right? Only the second demux is enabled. In that 0 0 means data available in fourth position, 0 1 means fifth position, 1 0 means sixth position, 1 1 means seventh position, right? These remainings are zeros, are not enabled. This demux 2 is disabled, only 3 is enabled, 4 and 5 also disabled, right? In this we discuss 0 0, 4 combination, 0 1 also 4 combination. Then we'll go for 1 0, another 2 combinations available, 1 0. If it is 1 0, what happened? 1 0 means demux 4 will be enabled, that is we got the data from D8 to D11, right? 1 0, and then again it is based on these 4 selection lines. 0 0 means 9th position, 0 1 means 10th position, 1 0 means 11th position, sorry 8th, this is 8th position, 9th position, 10th and 11th position. This demux 2 is disabled, demux 3 also disabled, only demux 4 is enabled, demux 5 also disabled, right? So it will enable only demux 4, that is got the data from D8 to D11. So one more combination available, 1 1. If it is 1 1, demux 5 is enabled, we got the data from D12 to D15. Again in the selection line S0 and S1, 0 0 means data available in 12th position, 1 0 1 means 13th position, 1 0 means 14th position, 1 1 means 15th position. This demux 2, demux 3, demux 4 is disabled, only demux 5 is enabled. We got the 4 different output based on this selection line, right? So this is the implementation of 1:6 multiplexer. We have got the 16 different output by using 4 demux, 1:4 demux. There are 4 demux, right? So in this video we discuss implementation of 1:16 demultiplexer using 1:4 demultiplexer. We discuss the design procedure, logic diagram and truth table. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the implementation of combinational logic using demultiplexer. Example 1, full subtractor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Implementation of combinational logic using demultiplexer. Here we are going to implement the full subtractor using the demultiplexer. So in the first step we need to write the truth table of the full subtractor. Then we need to represent the full subtractor in the min term form, because in multiplexer we get the min term as a output, right? Now we'll see the truth table of the full subtractor. So the full subtractor, the two terms available, a and b. Input is a and b, and borrow from the previous digit, borrow in, b in. So totally 3 inputs, a, b, borrow in, right? Then the output is difference between this and borrow out. What is borrow out for next digit? So a, b, borrow in 3 inputs, difference and borrow out is the 2 outputs. So because of 3, a, b, b in 3 combination, 2 to the power 3, there are 8 combinations are available, 0, 0, 0, 0, 0, 1 up to 1, 1, 1, right? Suppose a 0, b 0 and borrow 0, all are 0 means difference is 0 and borrow out also 0. 0, 0, 1, right? What happens? 0 minus 0 is 0. 0 minus 1. What happens? 0 minus 1. Here the 0 is there. 1. We need to subtract 0 from 1. Subtract. What happened? This is more number. This is lesser number. We need to borrow from previous digit. While borrow it become 10. 10 means 2 in decimal. So 2 minus 1 is 1. So the difference is 1 and borrow also 1. We borrow 1 from previous digit and difference also 1. So 0 minus 1 means we cannot subtract. So we need to borrow from previous digit. While borrow 1 from previous digit, 1 0 become 10. 10 means 2. 2 minus 1, 1. So the difference is 1 and borrow also 1, right? So 0 minus 1 means difference is 1 and borrow also 1. Here is same thing, 0 minus 1. So next third one is 0 already, so no problem. So 0 minus 1 means 1, 1. Difference is 1 and borrow also 1. Here 0 minus 1 means difference is 1 and borrow is 1, but here one more 1 is there. So this 1 minus 1 become 0. Only borrow is 1. 1 minus 0 and 1 minus 0, nothing will happen. The difference is 1, borrow is 0. Here 1 minus 0, again 1 minus 1. 1 minus 1 means difference also 0, borrow also 0. Here also 1 minus 1. Difference is 0, borrow is 0. Here 1 minus 1. Both are 0. But 0 minus 1 become 1, 1. 0 minus 1 means difference 1, borrow 1. Right. So now we completed the truth table. Right. So AB borrow in 3 inputs, difference borrow 2 outputs. Now this is represented, this 0, 0, 0, 0, 0, 1 is represented in min term, M0, M1, M2, M3, M4, M5, M6 and M7. So this is represented in min terms. This corresponding 0, 0, 0, 0, 0, 1, 0, 1, 0. Right. So the difference we have here 1 is available. 1, 2, 3, 4 ones are available. That is corresponding M1, M2, M4 and M7. These 4 are available as high level. So that is the required terms for generating the difference. That is sum of min term 1, 2, 4, 7. This is 1, 2, 4, 7. Right. So difference equal to the logical expression in terms of min terms is given as sum of min term 1, 2, 4, 7. In case of borrow out, again this is 1, 2, 3 and 7. So 1, 2, 3, 7 is available for borrow out. Right. 1, 2, 4, 7 we need a required output for difference. 1, 2, 3, 7 is the required output for borrow out. Right. Now we have the truth table. From that we got the logical expression for difference and borrow in terms of min terms. Right. In terms of min terms. Right. Now we need to go for the demultiplexer. We need to implement with the demultiplexer. We know that demultiplexer is 1 input 2 to the power n output and n selection lines. This one output is converted into 2 to the power n outputs by using the selection line. The selection line will decide 2 to the power n outputs. That is the demultiplexer logic. One input, 2 to the power n outputs and n selection lines. Here the 3 variables available. A, B, borrow in. So A, B, C or A, B, borrow in. So 1 is to 2 to the power 3 we need. That is 1 is to 8 multiplexer is needed. In that what we have? We need 3 selection lines. We need 3 selection lines, right? So we need 1 is to 8 multiplexer. That means there are 3 selection lines will be available. What is these 3 selection lines? 3 selection line is nothing but ABC. That is AB borrow in, right? What is the one input? One input is 1. The input is the data in is there. We'll give 1 as a input. So that we'll got 8 different outputs. The input is given as 1. The selection line is given as AB and borrow in. We'll get 8 different output. In that we need only 1, 2, 4, 7 for difference. 1, 2, 3, 7 for borrow out. Right? All 8 outputs will be available. In that we need to connect 1, 2, 4, 7 for difference. 1, 2, 3, 7 for borrow out. Right? What is this? Sum of min term. Sum. This is sum. So we need to add. So we need one OR gate here. 1, 2, 4, 7s are connected in OR gate, so that we'll get sum of min term. Here also we need one more OR gate. Now we'll see the logical diagram for implementing full subtractor using the demultiplexer. Right. So this is the 1:8 demux. One input and 8 outputs are available. This is the selection line. A, B, C or A, B borrow in. Right. So 0, 0, 0 means we'll get Y0 as a output. 0, 0, 1 means Y1 as a output. Other things are 0. 0, 1, 0 means Y2. 0, 1, 1 means Y3. Similarly, 1, 0, 0 means Y4. 1, 0, 1 means Y5. 1, 1, 0 means Y6. 1, 1, 1 means Y7. According to the input, we'll get. So that is available in our truth table also. Right? So these 8 outputs will be available, but we need for a difference, what we need is 1, 2, 4, 7. Right? So this 1 is connected, 2 is connected, and 4 is connected, and 7 is connected. Right? 1, 2, 4, 7. These 4 inputs are connected. We are not connected. Why not? Why not is not required. So this is OR gate. So sum of min terms. These 3, 4 terms are added together. We'll get the difference. So here we'll get the difference of the full subtractor. Similarly, for bar out, what we need? 1, 2, 3, 7. Right? So this 1 is connected. Here 2 is connected. Then 3 is connected. Then 7 is connected. Right? So 1, 2, 3, 7. So here we got the, this is the sum of min terms. So OR gate we are used. We got the borrow out. Right? So we implemented the full subtractor using demultiplexer. Data in is 1. Selection line is nothing but 3 inputs. A, B, borrow in. The 8 different outputs available. Based on the truth table, difference mean we need the sum of min term 1, 2, 4, 7. This 1, 2, 4, 7 is connected together. For borrow out, what we need? 1, 2, 3, 7. So 1, 2, 3, 7 connected, we got the borrow out. So in this video, we discuss how to implement the full subtractor using the demultiplexer. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the implementation of Boolean function using the demultiplexer. Example 2. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Implementation of Boolean function using the demultiplexer. Here 2 functions are given, f1 and f2. 3 variables. The input is 3 variables, A, B, C. That is given as sum of min term. F1, the function F1 having the min term 0, 3, 7. Only these 3 min terms are given for function F1. Similarly, function F2 need a sum of min term 1, 2 and 5. Right. These 2 functions we need to implement with the demultiplexer. We know that demultiplexer is nothing but one input with 2 to the power n outputs and n selection lines. So this is the basic structure of the demultiplexer. Having only one input that is converted into 2 to the power n outputs, that is done by the selection line. The selection line convert one input into 2 to the power n outputs. Right. Here n is 3. There are 3 variables available. So 1 is to 2 to the power 3. That is 1 is to 8 multiplexer we need. Similarly, we need 3 selection lines. Right. So to implement this function f1 and f2, we need 1 is to 8 multiplexer and 3 with 3 selection lines are needed. What is this 3 selection line? These 3 selection line is nothing but ABC. 3 selection lines are ABC. What is the one input? One input is 1, logic 1. Right. So we got 8 different outputs will be available. For example, 8, 2 to the power 3, 3 variable means 8 combinations, 0, 0, 0, 0, 0, 1 like that. In that 8 combination, F1 require only 0, 3, 7. This is sum of min term. So 0, 3, 7 should be connected in one OR gate. So that this OR gate will add these 3 min terms. Similarly, here we need one more OR gate. We need to connect 1, 2 and 5, right? So now we'll see the logic diagram. So we have the logical expression. Based on that, we decided 1:8 multiplexer is needed with 3 selection line. 3 selection line is ABC. Input is logical 1. 8 different outputs available. In that, we need to connect these corresponding inputs. Right, now we'll go to the logical diagram. So this is the 1:8 multiplexer, DMUX, 1:8 DMUX. The D is given as 1. The D is given as the 1, logical 1. These are all 3 selection lines. Based on the value of the selection line, the output will be produced. For example, 0, 0, 0. A, B, C, 0, 0, 0 means Y0 will be available. Y0 will produce the output. This 1 will be available in Y0. All other terms will be 0. If it is ABC is 0, 0, 1, then Y1 will be produce the output. Other terms are 0. Similarly, 0, 1, 0 means Y2 will be produce the output. 0, 1, 1, Y3 will produce the output. 1, 0, 0, Y4 will produce the output. 1, 0, 1, Y5 will produce the output. 1, 1, 0, Y6. 1, 1, 1 means Y7. So these 3 selection line will decide which output will be higher and which are the other outputs are lower. 0, 0 means only Y0 will be higher, 1. All other terms will be 0. Right. Now we got the 8 different outputs. In that function 1, what we need only 0, 3, 7. Right. So 0 is available. So this is sum of min term. So we are using OR gate, one OR gate. So here we need to add 0, 3, 7. So 0 is connected and 3 is connected. Similarly, 7 is connected. 0, 3, 7s are connected. So that these 3 will be added together, sum of min term, we got the function F1. Similarly, function F2, what we need? 1, 2, 5. So we connected 1. 1 is connected, then 2 is connected, then 5 is connected. So these 3 inputs are connected. So it will give the sum of min term 1 to 5, function F2. Right. So we got the output by using this 1:8 multiplexer, demultiplexer. We got the logical function F1 and F2. Right. So in this video we discuss how to implement demultiplexer for a logical function. Here the description is available. With D in, input is 1. Demultiplexer gives min terms at the output. Min terms means 0, 1, 2 up to 7. So by logically ORing means sum of min term. By using OR gate, the required min terms we can implement. Required min term means for function we need 0, 3, 7. For function 2 we need 1, 2, 5. Right? That is 1, 2, 5. The required min terms are implemented, so that we can get the Boolean function F1 and F2. So here we discuss how to implement the demultiplexer for a given Boolean function. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.